Good evening, sir. Today I am going to present our work on thermomechanical interaction between TSV and active devices in 3D IC packaging. I am Ankit Kumar and this work is done along with my teammates Jeel Patel, Meet Halpati and Vaibhav Shukla. So let's move to the second slide, problem statement, motivation and objective. So the first, what is the problem statement? In 3D integrated circuit, TSV acts as vertical interconnect between stacked dies. During fabrication, TSV heated around 275 degrees Celsius and cooled down to room temperature. Because of this mismatch in thermal expansion between copper and silicon, a significant residual stress is generated in the surrounding region. Now coming to the motivation. This TSV induces stress spreads in silicon and reaches the nearby transistors. Due to the piezoresistive effect, it changes the carrier mobility in transistor channel, and because of that, it directly affects the performance and timing and reliability of 3D ICs. Finally, the objective of our work is to analyze quantified TSV induced thermomechanical stress and its effect on carrier mobility using simulation and model from the literature. Now coming to this slide 3, literature review paper 1. So this paper focuses on device level impact on TSV stress on P MOSFET. The author used finite element analysis with global local submodeling to capture stress distribution on nano scale. So the figure over here shows the layout of P MOSFET with embedded silicon germanium stressor. The figure helps us to understand the stress is acting directly in the channel region of the transistor. Due to TSV fabrication, residual stress develops which affect the carrier mobility. Now in this figure author shows how mobility changes due to TSV stress. We can see the mobility either increase or decrease depending on the TSV diameter, gate width. The TSV variation is around minus 1.2% to 0.8%. Also, silicon germanium stressors improve the mobility, but TSV stress can degrade it. So overall, this paper proved that TSV stress directly affect the transistor performance. Now I will discuss the second paper by Jung et al., which focuses on the TSV stress aware full chip reliability analysis. So coming to the simulation setup, they considered a TSV structure with copper and SiO2 liner and applied temperature changes from 275 to 25 degrees Celsius, which generates stress due to CT mismatch between copper and silicon. Instead of full chip FEA, they used linear superposition of a stress tensor, which is faster and accurate. They uses von Mises criteria, which failure limit is around 600 megapascal. So coming to the key finding of the paper, stress is the highest at TSV liner interface. It ranges around 600 to 1200 megapascal. SiO2 liner acts as buffer and reduces stress. A stress decreases with distance, that is inversely proportional to a square of the distance. Regular TSV placement results in lower stress and irregular placement results in higher stress. So as we can see, Jung et al. It ranges from 600 to stress ranges from 600 to 1200 megapascal, but in our model we considered 90 megapascal. This difference is because we considered only TSV, while their work include full chip package effect. So some design insight is like increasing the thickness reduces the stress. KOZ defined safe region for the device placement. Softer material like BCB further reduces the stress. So overall, paper shows that TSV stress strongly affect the full chip reliability, and also proper design optimization is necessary.
Now I will discuss the third paper by Tian et al., which focuses on microstructure based stress analysis in through silicon vias. In the simulation step, they used focused ion beam scanning electron microscope cross section along with electron backscatter diffraction to map real copper grain structure. Then they performed finite element analysis in Abacus with anisotropic material behavior and applied thermal cycling from minus 55 degrees Celsius to plus 150 degrees Celsius for 200 cycles to study fatigue damage. Now coming to the key finding of this paper, the maximum stress is about 262 megapascal at TSV corners. From the box on the right side that is here, we can see that grain orientation strongly affect fatigue damage. Less than 100 orientation gives lowest plastic work around 26 megapascal, while random grain orientation gives high damage around 33 megapascal. Also, grain size effect, more grains means finer grains, which reduces fatigue because grain boundaries restrict dislocation movement. Now coming to the model comparison box, which is here, model difference versus our simulation. Their model consider anisotropic copper grains, crystal plasticity and thermal cycling, which result in higher stress value. But our model uses isotropic copper and single cooling steps. So our stress is around 90 megapascal, which is lower. Finally, relevant to our project, our model underestimates stress because it ignores grain level and isotropic. But our stress values are still valid for mobility calculation. So overall, this paper shows that grain structure and orientation play a critical role in reliability of TSVs. Now I will discuss the fourth paper by Jung et al., which focuses on full chip and package level stress analysis in TSV system. In simulation setup, they use lateral and vertical linear superposition and extended the model to include micro bumps and package bumps. They considered a multi-die stack with TSVs, micro bumps, and package substrate with temperature change of minus 250 degrees Celsius. Now coming to the key finding of this research paper, without package bump, the stress is around 100 to 200 megapascal, which with package bumps, stress increases to 800 to 950 megapascal. This clearly shows that package bumps significantly amplifies the stress. Also, the bottom die is most affected. Stress is highest near package bump edges. Increasing distance from bump reduces stresses. Now coming to the right side box here, our model shows around 90 megapascal stress, but when package bumps are added, stress increases drastically to 800 to 950 megapascal. Now model difference box, which is here. Our simulation include only silicon dioxide, copper TSVs, and no package level component. It does not include microbumps, package bumps, substrate or indel field which dominate real stress behavior. Finally, relevance to our project. This explains why our result is lower than literature and shows that full package modeling is necessary for accurate stress prediction. Now in the last, I am going to compare or summarize the research paper. So overall, these studies shows that both microstructure effects and package level effects are essential to accurately predict stress and reliability in TSVs based systems.
So the simulation methodology consisting of three steps. Step 1 is gauge geometry. So we have modeled it in the Fusion 360. As for the second step, we have done the SimScale Thermo-Mechanical transient analysis, which is a cloud-based software. And step 3 is the post-processing, in which we have plotted the graph for the von Mises stress and Cauchy stress in X, Y, and Z directions. So the gauge geometry consisting of the bottom layer, which is the bulk silicon, above which there is a silicon layer which is called Si1, and in which one cylindrical copper is there of radius 5 mm, and surrounding it is the SiO2 layer which is annular in shape and has the 0.5 mm layer thickness. After that, above it is the SiO2 layer for the dielectric, and at the top of the geometry there is a landing pad which is of the dimension 8 by 8 and 1 mm thickness. As for the simulation, what we have done is that for the boundary condition we have applied the fixed boundary condition at the bottom of the geometry, and for the initial condition we have taken 275 degrees Celsius for the all part of the geometry, and it is taken due to the considering that the initial temperature is for the annealing and then it is cooling down to the ambient temperature of 25 degrees Celsius. And here is the right side consisting of two figures. The upper one is for the CAD model and the bottom one is the result showing the von Mises stress in the SimScale. The result from the simulation showed that the von Mises stress is maximum at the TSV and SiO2 liner, which is 90 megapascal. As for the longitudinal stress, which is in x direction, for the Cauchy stress, its value is minus 11.46 megapascal at distance of 5 mm from the center of the TSV. Same for the same distance in the z direction, the Cauchy stress value is positive 23.51 megapascal, and in the y direction it is negative of 30.05 megapascal. Mobility indicates the change in the performance of the transistor caused by the stress induced near the location for a particular distance from the TSV. And here the simulation indicate that for our case it is positive of 2.34 percentage, uh, which is comparable with the what we got in the research paper. It is indicating minus 1.2 to plus 0.8 in paper 1. As for why there is a discrepancy in it is, the first is the loading method. So we have applied the thermal cooling, uh, for which the paper are using the tensile residual stresses. Second one is the liner thickness. So in our case, the liner thickness of the SiO2 layer is uh, 500 nanometer, but in the paper it is 125 to 200 nanometer. So thinner is the liner, it will cause more stress, and so it will cause the lower von Mises stresses. That's why we got our von Mises stresses a bit less compared to the mentioned in the paper. Third is the no package bump. So paper 2 and 4 indicate if we include the bumps, then this total stress will go up high, like up to 200 to 400 megapascals. Fourth one is the isotropic copper. So we have in the simulation, we have considered the copper as a isotropic case, but in the research paper they are doing the experiment for the anisotropic green model. And the fifth one is the single event versus the cyclic. So paper 3 uses the 200 thermal cycle accumulating fatigue plastic work, but we have considered only for the single case which is at constant temperature, not the cycling load.
So now we'll demonstrate the ML model for rest of the analysis. So first of all, this is fundamentally non-ML problem. So why are we using ML? So first problem is that computational bottleneck. So for each of the simulation, it took about 8 minutes and about 3 lakhs node points. So it's computationally heavy. So this physics-assisted ML, the surrogate kind of model, can be helpful in design space explorations. So while optimizing 3D IC layouts requires evaluation of hundred of parameters like TSV diameter, array pitch, liner thickness, etc. So full FEA analysis for each iteration is impractical. So this approach can be helpful for that. So we'll be demonstrating the framework approach. So how we can implement this surrogate machine learning kind of framework to instantly predict the behavior of mobility change. So for data generation to train our ML model, we created this quarter model kind of things. So this quarter model, we can apply symmetrical boundary conditions on this flat faces. So it will save about 75% of computational cost. Um, and also we'll calculate the Cauchy stresses in X, Y, and Z directions. And then we'll use the equation from the literature for calculating the mobility loss. So we'll take calculate this mobility loss on grid from 5 micrometer to 30 micrometer on fixed 1 micrometer grid. So this here are total our data points. So that is it. So we are using random forest regressor for our as our machine learning model. So our input features are TSV diameter, um, liner thickness, TSV depth, array pitch, and annealing temperature. And we are taking output as an entire mobility degradation curve. So results, prediction, and conclusions. So the model successfully learns the physical trend and it gives the mobility behavior in less than 1 second. So here you can see this is the model prediction in top, and this is the 3D 3D FEM simulation. So from 5 micrometer to 30 micrometers, so behavior is quite similar. So root mean square error and mean absolute error is actually quite good. But one drawback is it has negative R square score. So because there is scarcity of data, so there isn't enough data because there was a generation limit. So future scope could be the dataset can be scaled with automated batch FEM runs and better models like deep neural networks for full chip can be used. So to conclude our presentation, so we validated physics modeling. We did the 3D FEA analysis of complete substrate with TSV and compare the result with the literature, which was quite good. We addressed the bottleneck, that is the computational time is quite high. So, and we provided the solution that rapid AI surrogate model uh, that can give the outputs in less than 1 second. That enables the rapid design space exploration in advanced 3D IC packaging. These are the references below. Thank you.